Our closing keynote today is Gabriel Dos Reis, who's going to tell us about C++ modules in the year 2021. Hey, Gabby, welcome.
Hello. Hello from Seattle, or Redmond, I should say.
Yeah, it's great to have you closing out the conference. Did you close out the conference again last year? I can't remember. Wait, you had another great talk last year, but I can't remember which session it was.
I think that must have been at meeting C++ 2020. Yes, it was closing keynote.
Yeah, cool. Well, thank you so much. And everybody, Gabby.
Yeah, glad to be here. Okay, so I want to just give you a quick update on where we are with C++ modules this year 2021. So you probably already watched Daniela's talk. If you haven't, please do right after my really go and watch her talk. It's fantastic. Let me give you a quick 30,000 feet above view of what modules are. Essentially, they're language constructs that allow you to clearly specify the interface of your components. So here, I have basic component that gives you a rectangle. I call it modules basic plane figures. You have a point, have a rectangle, and then we have utility functions that give you the width, height, and an area of a rectangle. So with modules, you can just specify directly what is needed for the consumer of your component. And this is it, simple. And how can you use this stuff? Equally simple. Instead of having some kind of include file, you just say import the module name, and then you proceed to write your code as if that import had been some include. So those two things are the basic things that you need to know about modules, nothing else. How this actually gets compiled depends on the compiler. Each compiler has its own flags and so forth. But this basic semantics at the C++ level is quite the same. So what are they really? They're a C++ 20 features. What do they give you? They provide you componentization. You can, as I showed earlier, you can delimit very clearly the abstraction boundaries of your component. Here, when I say export module basic plane figures, I'm saying explicitly I want points, the types points, rectangle, and the three functions to be usable. If I've had declared any other functions here that wasn't at all preceded with the keyword export, that function will not be usable from the outside. So you have a language means to say these are the boundaries of my components. They give you isolation primarily from macros, evil macros. With named modules, if you define a macro before you do an import, that macro, its existence is not at all observed by the boundaries, within the boundaries of your modules. And similarly, if you happen to use macros, God forbid, you happen to use defined macros within your named module, they will not be seen from the outside, which is good. The third is because modules bring this kind of structure, it makes structure available to the compiler to exploit. So you benefit from the hygiene, you benefit build throughput. In some of the testing, I've seen speed up varying from 5 times to 10 times. And yesterday, a friend of mine was actually showing me a program, real-world program, where he got 42 times, not percent, 42 times X factor speed up. So that is what modules bring you. And the fourth thing that they gave you, which is quite interesting for C++ in the modern era, is that now you get to enjoy semantics-aware developer tools. An example of that is, imagine you want to provide binding between your C++ libraries and some other, foreign language like the Python, JavaScript, or you name it, right? So now you get tools to do that. I'll show you later how that's possible. In aggregate, modules provide an alternative that's far superior to hash includes and associated hack arrays that you get. And so we have this new world, which is, you can, imagine our array of macros. And today we are with hash includes. The question that often asked is, how do we get there? What is there any transitional path from this messy world we are in today to the bright new future tomorrow? And the answer is yes. Though the spec for modules come with at least two ways of transitioning from the messy hash includes to the better structured modules, the global module fragments and header units. I would say, shortly a few things about those. So before I move on to the next issue, I wanted to just have you see clearly what is happening here. In conventional software development, you usually have this notion that you have a separation between interface and implementation. So the module keywords and image feature gives you this, this feature where you can say, this is, on the left-hand side here, you see clearly the interface of your components. And on the right side, you see the implementation of the functions that the period implementation are not particularly interesting to the consumer. So you have this clear separation. You put them in two different files, and just like you used to do today, where you have header files and .cpp file, you can continue doing that today, tomorrow, or even today, I'll say, where you have the interface definition in a separate file, and then you have the implementations elsewhere. But that is not required. So if you just want to have one single file where you put both the implementation and the interface, and then relying on this isolation, you can just do that. Right here, you have just one single source file that contains both the specification of the interface and the implementation of a function with its an array. So this is something to keep in mind if you work with what people call single header, header only libraries, where we just have one single file that contains everything. The additional feature that you get with modules is that they allow you to hide implementation details, which you can't do with header files. Okay, so where are we today? So like today, you have several efforts going on. You have, in terms of compilers, you have the three big compilers, MSVC, GCC, and Clang. So MSVC has an implementation which is production use ready, meaning that today I'm telling you, you can go and start using modules in MSVC for production. GCC was released last week, so just fresh out of the oven. It contains a preliminary implementation of modules, or in C++ 20 mode, you need an additional flag. But the implementation there is why it is labeled experimental. You can still try it in non-critical production use and see what's going on, and give feedback to the GCC developers. They really love to have feedback and the users and bugs that people find. And then in Clang, there is a branch of Clang that contains an active development of this feature that is already in C++ 20. Just like GCC, it is also experimental. You can check the source code out from Ian Sando's GitHub page and build and enjoy modules. I really encourage you to try modules in these three compilers to get a sense of it, to get prepared. I suspect by the end of this year and early next year, you some of these experimental mode will turn into production ready features. So that is the situation today in terms of compilers. MSVC gives you production ready implementation. GCC has modules in GCC 11, which was released last week, but it's labeled experimental. So once you have your compilers, the next thing you want is how do I build programs with this new fancy feature? Well, for build tools, you have MS Build, which has support for modules. And if you want to know how to use modules with MS Build, given the length of this talk, I encourage you to go and look at these three documentations. So a blog post by Will, which gives you an overview of C++ modules in Visual Studio. Right, in the IDE, integration in the IDE and toolset. On the documentation page, the Microsoft documentation page, you have a walkthrough of how to build and use header units in MSVC, and also how you can import standard library headers in your code. So header units are some amalgamation of named module, real modules, and header files. So essentially, they're header files that you import, meaning you try to use them as if they're modules. They're not really modules. They don't give you the isolation semantics that you get from named modules. You just get some of the performance benefit, which is where it is quite interesting. CMake has an experimental support for modules. It's really experimental. If you want to enable it, then you need actually to use a CMake macro that has experimental in the name. Build2 is another build system, build toolchain that has had that was among the first to have support for C++ modules. Boris Kolpachev has really nice tutorials and documentations about Build2 support. Build2 is, it's being developed very actively, so things change quite fast. But everything that has released so far is pretty good. And very recently, the Maison build system has also added experimental support for modules. So here you have 4 build systems, 3 compilers, and you can use them in combination today. Like, you don't have to wait a year. They can try them today and experiment and build programs, get a sense of how to simplify your development, how to make you more productive. And the other thing that I want to mention is, of course, you have the compilers, have the build systems, and how do you use them? Last year, as I was mentioning earlier, I gave a talk at TPPCon. You can watch video, more complete overview of how to program with modules. Daniela Unger just explained, some of the key technical aspects that I've worked hard to put behind the scene, but the key foundation, she called them the spices of what make modules very tasty. And of course, I mentioned Build2 earlier. Boris Kolpachev last year also gave a talk at TPPCon on practical C++ modules. And finally, I have this keynote on what it means to program with C++ 20. Like, this is really new language. It's really, really new language, and what you can expect from your compilers. Okay, so please go and try. You have the compilers, build tools, and then you have educational materials. And if you have any question, please give feedback. Now, the other aspect that I wanted to touch upon is that modules are actually a tooling opportunity. It is outstanding that C++ has succeeded in spite of what I would call the paucity of developer tools, semantics over developer tools. If you look at languages like, let's say, Python or Java or C Sharp, they come with a rich ecosystem of developer tools, semantics-based developer tools, around them. And for C++, it has been really, really difficult. But thankfully, thanks to module, things are changing. So with modules, one thing that changed the game of compiling and using modules is that now you have a clear separation of interface from the implementation. You're telling the compiler, this is what everybody else needs in order to use this component. So what a compiler will do when it's compiling your interface is produce a complete semantics representation of your input source code, characters into a rich semantic data structure, which is the semantic representation. And every time you import module, it will reuse that representation. That is why using module is so fast. Like, you don't have to do the same work over and over. No, just once. The reuse of semantic representation, right? And on the other side, one of the problem is that this representation is compiler dependent. Today, SVC has its own representation, GCC has its own, which is very different from the representation that Clang has. One thing that I would like to see happen, going forward, is that all these major compilers somehow find ways to give access to that representation that they all produce. Right? If you have three compilers, they compile the same module, they will get three different representations. That's just insane, right? We just need one representation because we have only one program. So what they can be used for, this semantic rich data structure gives you access to the same content, but this time you no longer need a C++ compiler to understand it. You just need any dumb script or program that can traverse a graph. That's all you need, because the compiler has already done the work of turning your stream of characters into data structures that have semantics to them, right? And by getting access to that representation, what we're doing now is that we have the opportunity to give to the masses, to the, 5 millions of C++ developers, access to the higher levels of C++ representation, right? If you want to interface your library with a, component written in a different language, most of the time people will use extern C. Those are the lower levels. Like, anything that's extern C says, basically forget about type checking, a bunch of other nice things that C++ gives you, right? That's just insane. We want to change that, and we have the opportunity to change that. So this rich representation can be used to generate a bunch of other, data for tools. We saw earlier, talk on safety checking, runtime safety checking. Now you actually have a data structure that can aid that representation. If you want to do runtime JIT, you can use this representation to do that. You can defer code generation to program runtime so that you can collect more data, runtime data, use that to inform code generation, right? If you want to do type-safe distributed computation, you're doing computation, you want to farm, distribute, some part of computation to other machines, you can take your data structures, very rich, and then marshal them and then send them over network to the other machines. And you can do that because now you have a safe representation of the rich data structure that you're using. And by doing that, you just realize that you can actually expose um, APIs in C++ that use the higher levels of abstraction of C++ with other languages. You don't need to go to the, external C bug-ridden aspects of the language. So concretely, what does that mean? With the MSVC toolset, for example, the representation, we call it an IFC. When you have a module interface, you give it to the MSVC front end. You evoke cl.exe on that interface file. It's going to produce two things: the metadata, which is stored in an IFC file, has a suffix.ifc, and then the object code that gets linked to the rest, right? So this interface file is, the format is used to compile the module primary interface, partition interface, internal partition file, and also header units. These strange header file that turn into some kind of modules, right? And the binary format is quite simple. It is structured based on the principles of what I call the IPR, which is work that Bjarne Strustrup and myself did about 15 years ago, right? Time flies quite quickly. So with the IPR, you have a complete representation of what C++ is. It doesn't give you access to all the syntax ceremony. No, it gives you access to the rich semantics, right? And that is what you need for most of these things. It is quite compact. The consistently in all the tests, and whether it is synthetic or production use, we found that the IFC files are at least an order of magnitude smaller than the PCHs that MSVC will produce conventionally through the conventional switches. So you get an order of magnitude saving there, and they are very easy to process. They are not memory dumped. They're on disk representation of rich data structures, and all you need to do is, how do I traverse a graph? That's basic things that we do all day, for everything that we do. So how does an IFC file look like? What does it look like? It's quite simple. It starts with 4 bytes, and then it has a header, and then header describes the names of the module it is for. We would say header units, and the architecture, and a bunch of other compiler flags and so forth. And then it gives you some kind of forward reference to partitions. So partitions are just homogeneous tables used to represent each entity needed in a declaration, whether it is a type, a declaration, a context per function, and so forth. And of course, each of those entities have names. So you have a big string table that contains all the names that are in your source file, names and the strings and so forth. And near the end of the IFC file, you have what we call the table of content. The table of content is just an array of back references that tells you, here is the partition N, which its name, and how many entries there are, and what is the size in bytes of each entry in that partition. So quite simple. The structure of the IFC file, as I said, is very simple. It's just a bunch of homogeneous arrays. That's all it is. And you do graph traversal on that. If you want to know, because of the time limit, if you want to know more about IFC structure, there is an upcoming full description open to the C++ community. And along with that, I hope we'll also get tooling libraries. And I gave a more extensive explanation of the structures in my keynote last year, closing keynote at Meeting C++. So you can click on the link and watch it. And that was followed by a live Q&A. And you can also see what kind of questions that are asked here. If that's an answer, some of the questions have, please drop me an email. Don't hesitate to drop me an email. So what I want you to do today, given where we are, I want you to go and download, acquire those compilers, your favorite compilers from the three, like MSVC, Clang, and GCC. All three have some implementation of the C++20 feature modules. MSVC comes with it production ready. Clang has it, so GCC has it in GCC 11, and Clang you have to acquire it from a branch, and hopefully that will migrate to the main development branch. And try any of these build systems that I hope you're using one of these for, right? And what I need from you is provide feedback to the C++ committee in terms of why we really need standard library modules. I know I've signed up for helping with that, but sometimes WG21 needs some kind of encouragement to do the right thing. Also, please provide feedback to your favorite C++ tools providers on making accessible the build artifact, these build module, interface files, so that you can build tools on top of them. They need this kind of feedback and encouragement. With that, I'm ready to take questions.
Great. Thank you so much, Gabby. That was really great. Modules are something that I'm really excited about, and it's always great to have, here's where we are and where we want to go. So we do have some questions in chat for you. Mm-hmm. One is, so I put up a poll in chat asking people whether they plan to use modules in production, mm-hmm. Or if it was a maybe, or if it was no. Most are yes, we plan to, or yes, we're doing. So some people said maybe, and one was that one big question mark for them is the state of the IDE and the whole pipeline support, IntelliSense, dump files, source indexing, things like that.
That's a good question. So Visual Studio, Visual C++ is the visual aspect of it. So now I think the previews that are available, I think 16.10 preview 2 or 3, and
2 is out now. 3 will be coming soon.
Okay, they have support for IntelliSense support for modules now. They started having it, and I would say every preview it gets even better and better. And I encourage everybody to try them out. It's really there.
Yeah, especially preview 3 will be coming soon, and preview 3 IntelliSense has come a long way in a lot of things.
Yes, I heard it has a lot of fixes, quality improvements. And please try them out. They are production ready. Please, don't hesitate.
Another question is the internal compiler data or IFC likely to play nicely with C++ reflection looking forward?
Oh, that's a great question. So I have been kind of, taking a step back because been very busy with the IFC. But my hope is that any C++ compiler that supports C++20 is going to have a representation of these things. So it is just natural that they will all jump on these representations to provide static reflection. For MSVC, I think the answer is yes. I don't write GCC code these days, but I would be very surprised if they went completely different ways and they don't reuse these data structures. With the IFCs, you don't, as long as you don't need to actually introspect the code in the same translation unit where you're asking the questions, you can use the IFCs to generate code that you compile at build time and link into your same program. So you can do some kind of build time reflection. It just won't be compile time in the sense that you ask the question for entities that are in the same translation unit. But if they're translation unit that are part of the same program, you can do that kind of build time reflection, which is already nice. And as an example, if you look at Qt, for example, it uses mock, and it needs some kind of meta, object protocol and that kind of stuff. So you can use the IFCs to replace a lot of the protocol stuff that, or at least provide a much better implementation of it. You don't need you wouldn't need Q object to macro to mark. You could just say, hey, give me that file and give me that type, or give me all the types that have these base class and so forth. And it worked with template nicely. So it is Mark on steroids.
Another question is about the Windows 10 SDK and providing modules, interface units to replace the old Windows headers.
Oh, okay. So that's more questionable for Windows, but I'll try to answer the best I can without stepping boundaries. So the Windows org has embarked on a new journey to provide different representation of Windows. What they call it now, they have a metadata description of Windows.h. And from what I know, I've seen that representation plays much nicer with modules than the old text-based Windows.h. Whether Windows.h itself will come as modules, I don't think that will happen. But what will happen is that from the API sets that they have on Windows, you're going to see coming online more and more components that are directly consumable as modules. But that's long-term planning. And first, they have to get the metadata representation of module Windows.h in first, which plays quite nicely with modules. And the next step is exposing the API sets as modules.
Yeah. Another question: if there is a common IAPR representation of a module, would it be reasonable to distribute that?
Yeah. So for me, the answer is unambiguously yes. I know there is a debate in the C++ community. Some people say, oh, they don't want to distribute. I think it is just a matter of time that as we start using modules more and more, we come to the realization that part of the benefit of module comes from reuse. Like if you want to do analysis like Sonny showed earlier, well, you have to save the IFCs and then you run your stuff on top of it. Right. And then the next, if you want to use the result analysis, you have to save that, or you have to package it in a way that it can be reused by the next component that depends on your modules, right? So the distributing the representation of module interface is just a matter of time. It's a necessity. It will just take us as a community time to realize that this is actually a good thing to do.
Yeah. All right, we're pretty much at time now, but there is one last question which I think people would be interested in, which is people have talked a lot about potential speed up of modules for compilation. What kind of speeds up are we seeing? Is module compilation getting reasonably optimized yet in MSVC?
So we have not yet spent a lot of time optimizing modules in MSVC. We've just been busy trying to get the functionality there. But what we see from just like the naive implementation is that we have between 5 to 10x factor X improvements in build time, right? I saw an example, like I said, I saw an example yesterday having to do with device drivers and all of that. Someone is telling me that they saw 42, if I get the numbers correctly, 42x improvement. So no, I don't expect that number to be uniform for everybody, but it is impressive.
Yeah, totally. Okay, well, thank you so much. That's us at time now. So thank you for your time, Gabby, and for your talk.
Thank you very much.
And we'll see you next time.
Bye.
Okay, well, we're about at the end of our time now, so thank you for everyone for joining. A few things before we finish up. We do have a survey which we would love you to fill in. I believe the link will be in chat in just a second. So please do fill out the survey. It helps us that if we run this next year, we can make the event even better. If you'd like to ask more questions to the speakers, we've got a couple of potential options for you. One is right here at Learn TV tomorrow. There's going to be an Ask the Expert segment with folks who have been here. And then the day after, there's going to be a Teams event in the Reactor, which is going to be a bit longer, an hour long, so you can do some deep dive questions there. So all of those links will be in the announcement section. So if you go and look at that in Learn TV, it'll all be there. But thank you so much for joining. Thank you to all of our speakers who are all wonderful today, and to everyone who produced the content for our pre-conference sessions. I'd also love to absolutely specially thank all of the folks from the events and production teams who have helped to put this all together and make sure that we're running and we have all the Q&A and we have things, because last year when I ran everything from my laptop, it was nightmare. So thank you everyone for doing that and for helping out. And I will see you next time we run an event like this. Bye.